It's 9 a.m. It's a beautiful Monday morning. Let's get started. Let's get right into it. I guess we can do Project 5 questions for a few minutes. Yes?
So if you have an assignment statement that is just, it's not a variable, it's an integer, like x equals 5.
Yes.
So do you, I'm assuming we also need to create a value node for that. It just won't have a name, it'll just have a value in it?
Yep.
Okay.
Yeah, the name actually, I have to check the compiler, but I don't think the name is actually ever used by the compiler.
Okay.
Right? The compiler doesn't care about what the IDs are of the value nodes. It just cares about copying values from one to the other.
And then as we use the same variable over and over, we're not creating a new value node for each one.
Exactly, yes, that is the key. You want to make sure that every reference to a value node, if it's the same variable, points to the same value node, right? That way, your assignment statements will be updated. Like when you see you have a print statement that refers to a variable, that assignment statement will see the same value. Yeah, that's the key to this project. And I guess I'll also reiterate, I think I said on the mailing list, you should not do any computation of the program in your front end. So you should not be if you see an assignment statement that says A is equal to 4, you should not copy 4 into the value of the value node A. That's all done by the back-end compiler. Right? You're not executing the program. You're just creating the intermediate representation so the back-end can execute it. Yes, there's another hand, yes.
So after an if statement is parsed, you have in the pseudocode saying to like append a statement list after the no-op node that you attach after the if statement.
Mm-hmm.
So after an if statement, there's another statement that's a no-op statement, and so in compiler.c, is it running that if statement, and then once it hits the no-op node, it's skipping not onto the next statement?
It'll be whatever the next statement is after the if statement. So you're creating like a pseudo no-op statement because you need to make sure that the true branch of the if statement, that its last instruction, the next of its instruction is that no-op statement. So basically, if you think of it like a tree, right, it branches, well, it's not a tree, but it branches, right, and so the if branch is going to do stuff, and then it needs to come back after it's done doing stuff to the thing after the if statement. So that's why you're creating this no-op statement there. So that way you set the last element of the true statement, the last statement in the true statements, you set its next value to be that no-op statement.
The last value.
Yes, this is how you have to do it to do nested loops. Because there may not be an instruction after, I guess in that case it wouldn't matter, but yeah, it makes things a lot easier. Cool. All right, 4 minutes. Very good. All right, let's get back to we're talking calling convention. So just to kind of recap from where we were on Friday, the x86 Linux calling convention, the CDECL, when a caller wants to call a function, their job is to first push onto the stack the arguments of the stack in right to left order. Then they're going to push the instruction, the address of the instruction to return to after the function call. And it's the job of the function that's being called to save the previous frame pointer onto the stack, because we're going to overwrite it. Then they're going to create space on the stack for local variables, ensure that the stack is consistent at a consistent location before it's returned, and then finally it puts the return value of the function in the EAX register. So if we look at some code, so we're going to look at a super simple program. So this is a function main, has a local variable a. It sets a equal to calling some function call e, passing the values 10 and 40, and it's going to return a. So this function call e is really easy. It just returns a plus b plus 1. Okay, I think that's a little better. So if you compile this and read the disassembly, you'll see it looks something like this. So obviously this depends on exactly what compiler and version you're using. So main first pushes EBP, it moves the stack pointer to the base pointer, it subtracts hex 18 from the stack pointer, it's going to move the value hex 28 into ESP plus 4, it's going to move the value hex A, which is 10, into ESP, it's going to call that function, call E, and then it's going to move EAX into EBP minus 4, and then move EBP minus 4 into EAX, which seems redundant. Then it's going to call leave and return instruction. So some important things that when you're looking at these function calls, so as we saw, right, every function in the CDECL calling convention has to save the previous caller's base pointer, and it has to create room on the stack for its local variables. So that's what happens in this with the function prolog. So this push EBP is storing whoever calls main's base pointer on the stack. And then it's setting up its own stack frame by saying, okay, wherever the stack currently is, set the base pointer to be wherever the stack currently is. And then it's subtracting 18 from the stack pointer, which is creating, well, hex 18. So it's creating space on the stack for main's local variables. So why is it creating hex 18? What is hex 18? Anybody? 24? Why 24? Is main's local variable size 24? What is the size of main's local variable? How many local variables does main have? What's the size of an integer? 4 bytes. How many bytes did it move it down? 24.
So just padding?
Partly. Well, let's keep that in mind and think about why when we look at the actual, we'll step through this to see exactly what's happening. We also have the epilogue of the function, right? So this leave and return, so leave does the complete opposite of these first two instructions. It sets the stack pointer to the current base pointer, and then it does a pop EBP, so it restores the saved base pointer. And this return is the instruction that says, goes back to whoever called main. So it takes the saved instruction pointer that's on the stack and starts executing from it. So the call E function is pretty easy. It does a push EBP. It moves the stack pointer to the base pointer. It moves EBP plus C into EAX. It moves EBP plus 8 into EDX. It adds EAX plus EDX, moves it into EAX. It adds 1 to EAX, and then it pops EBP and then returns. So this function too has the same thing. So it has an epilogue. Its epilogue is actually a little different. What is it not doing that main is doing? What is that? Yeah, so why? Why didn't, so it's this line's kind of different, but why did it not do that? Yeah, like the call E function has no local variables, right? So it actually doesn't need to create space on the stack for the local variables. So it has a prologue and an epilogue. The epilogue is slightly different. Instead of a leave, there's a pop EBP. This is just because of the fact that it doesn't have to do both of them. Okay, so let's step through this to see how this actually works. So we have our call E function, we have our main function, and when the program is compiled, the compiler will write out exactly in memory where the bytes of these instructions should be. So when I ran this, it just said that, hey, call E starts at 804, 8394 at all these bytes, and main starts at 804, 83, A5. And so let's say before we're executing this, the stack kind of looks like this. We have some registers here, and so let's say the top of our stack is at FD2D4. Right. So, and we know this because there is the value FD2D4 in the ESP register. So the fact, that's how we know exactly where the stack is. When we start executing main, do we know exactly what the value is inside this base pointer register? No, why not?
Depends on the previous program.
Depends on the previous program.
Previous function.
What do you mean? What's the difference?
Because it could be the same program. The compiler doesn't know.
Right, so, well, let's talk about, it's not the previous program. Every program when it executes has its own, I don't know, fresh copy of everything. Fresh copy of memory. Programs can't see each other's memory unless you specifically allow them to. So this is going, the value in here, right, is going to be whoever called main. Right, so you may think like, well, why, but main is the start of our program, right? So who would ever call main?
Might be like the OS or something.
Yeah, so it's actually libc has to do a bunch of, so when you call a libc function, it dynamically links to that file and that code at runtime. So a bunch of things happen to set up your program to be executed. You can actually write, if you write the assembly yourself, you can say start executing at main, and it will work. Will it work? Yeah, it'll work. But normally when you compile a program, there is some function that calls main. And if you do the disassembly, you can look and kind of see all that stuff. But we don't know what it is, we just know it's something, right? We know that there's some value in there. And then we know that the instruction pointer, when main is going to start executing, points is at 804, A3, A5. And we don't really know anything about the base pointer except, oh, that's the wrong value. Well, we don't know what it is, but we know it should be above our current stack pointer, right? Because there's some frame up else in the stack, and main's getting called, so main needs to make its function frame. So the first thing main's going to do, right, is to push the base pointer onto the stack, right? So whoever called main, it doesn't matter who it is, we're going to save that base pointer. Then we're going to change the current base pointer to be where the current stack pointer is. So this base pointer is somewhere up here. We're going to have this point to, so now the base pointer points to FD2D0, which is going to be right here. Then we're going to move the stack pointer down 24 bytes to allocate that space on the stack, right? And so the question should be, well, why are we doing that? So let's keep that in mind. So now, going back to the C code, what's the first thing that happens in this main function? Right? So the very first thing that's going to happen, right? Does this declaration do anything? No. Right? But the first thing that's going to happen is we're going to call this function. Right? This callee function. So we just created all of that. So we want to call a function. We have to look up, okay, how do we call a function in our calling convention? Well, we push onto the stack the arguments that we want to pass to this function from right to left. So here, so what's hex 28 in decimal? 40, right? So we're calling this function callee, and we're passing the values 10 and then 40. So here is the current stack pointer, right? And we need to push values onto the stack from right to left. So it's moving 40 to ESP plus 4, which is up here. And then it's going to move 10 on the current stack pointer, right? So we've set up, we're passing these values 40 and 10 to this function callee by putting them on the stack in this order. So if we go back to why did it subtract 24 bytes here? Well, it's actually doing some optimization. It's creating space for local variables, and it's changing the stack such that it can call this function without actually pushing and having to move the stack. So we can know based on the stack pointer exactly where to put the values onto the stack. Why specifically it does that, I don't know. It's got to be some kind of optimization thing. Okay. So why doesn't this say call callee for this instruction?
Because it doesn't know what callee is.
Yeah, it does. It's just a name that we gave some piece of memory, which is the start of a function, right? So when the program actually gets loaded, right, your linker resolves all the references so that our program says, hey, call 804.83.94, which should be that address of callee. So the call function does two things. It's going to change the instruction pointer so that it starts executing at whatever that address is, but it also pushes the next address that would have been executed onto the stack. Right? So a normal jump instruction just says go start executing there. Right? But a call instruction will put 804.83bf onto the stack. So this is also part of the calling convention. We pushed all the arguments, then we're going to push the return instruction of where we want to be executed when we come back. So let's see what happens. So it's going to push 804.83bf, which is this address, and then it's going to start executing this callee function. Now, callee just got called, right? It doesn't know who called it. It could have been main, it could have been one of 100 functions, right? It doesn't matter. But it knows that it's going to use a base pointer, so it's got to save the base pointer of whoever called it. So it's going to push fd to d0, which is main's base pointer onto the stack. It's going to set the current base pointer, so remember the base pointer right now is pointing to main's base pointer. It's going to change it to point to the current stack pointer. So now it's basically saying, okay, now I am the function that's executing, and I have my own base pointer. And now it needs to access those parameters, right? The callee function just returns a plus b plus 1, right? So using that convention, right, just like we saw that local variables are negative offsets of the base pointer, here parameters, because of the calling convention, if the base pointer is here, how does it get from this base pointer to the first parameter a?
By adding.
By what?
Adding.
How much? 4? 4 will get you here.
8.
8. Yeah, right? Because it knows that, okay, when I get called, I'm on the stack at this point. This is my base pointer. I know directly at that point is the saved base pointer of the function called me, right? Because I put that there. Then I know, according to the calling convention, above that is the instruction that I'm going to, the saved instruction pointer of the function who called me. And then above that is going to be the leftmost parameter, and then above that, the second most left parameter, and so forth, all the way up. So this function, when it gets compiled, it knows exactly, okay, if I want to get parameter 2, I know I have to do, I don't want to do the math, but it knows exactly what offsets to do. It's going to be a constant 8 plus whatever the size of all the other arguments are on the stack. So we've moved the stack pointer and the base pointer, so now the base pointer is also pointing down here. Now it's going to actually perform the computation, right? So it's going to say, okay, take EVP plus C. So plus C is going to be 12. It's going to be here, hex, the value 40. It's going to move that into EAX. But before that, right, so we think about function frames, right? We have the function frame for main up top, right? So this is main's function frame. And we have callee's function frame here, which contains all the parameters, and if it had any local variables here. So one of the key things here is, why is it laid out like this, like main callee? Why isn't it switched around? What does this represent, the fact that they're on top of each other like this?
The order in which the program actually executes.
Yes, the order that the functions were called in the current execution of the function, right? We know by just looking at these function frames that callee was called by main, and that main was called by whoever's function frame is above that, right? And if callee actually ended up calling main again, there would be another function frame for main on here, and if main called callee again, there would be another function frame for callee on there.
So if your program went main callee, then we wouldn't actually the memory wouldn't just rewrite over the first callee. It would actually allocate a separate.
Exactly, yes. Every invocation of a function gets its own space on the stack.
So what happens if the stack gets full? Is that what would create the Stack Overflow? Or
Exactly, yes. Right, so if you have a function that calls itself recursively, right, but the terminating conditions are bad, right, it's going to create, like, let's say if you had callee calling itself without any stop, it would keep trying to allocate space on the stack, and eventually you're going to get to memory that's not allocated. It'll throw an exception. I think on C it would throw a seg fault, but on Java it would throw a Stack Overflow. Or C#, I think, also does Stack Overflow. Yeah, so that's exactly where this comes from, right? Because we're not reusing memory, because every invocation of a function has to have its own chunk of memory, that if we just infinitely allocate functions, at some point we're going to run out of memory, right? We just can't have an infinite allocation of functions. Cool. So this is one of the key things I want you to get out of this, is the function frames and how function frames on the stack correspond to the execution trace of where that function is.
Question.
Yes.
Can we print that stack trace out?
Kind of. Actually, it's funny that you ask. I actually have a Fury student working on that right now, because I think it would be super useful to have in this class. Yes, you can do this, but you have to use the debugger, and you have to like print out the values of the stack, and you have to like create this thing. Like that's actually exactly what I did to do this, right? Is I like created this program, I stepped through it instruction by instruction, and made sure that everything was actually happening the way it was supposed to. The other thing you can do is you can also do it like we did here and just draw it, right? You can step through each of the assembly instructions and see, as long as you know exactly what every instruction does, then you can simulate what it's doing on like a PowerPoint computer in this case. Okay, so let's continue this, right? So now we're trying to execute the values a plus b plus 1. So we're going to move EBP plus c, which is b, right? It's the second parameter to this function, hex 28, which is decimal 40, into EAX. Then we're going to move EBP plus 8, which is a, or hex, sorry, it's 10, which is hex a. We're going to move that into EDX. This, I think I mentioned the load effective address is a really complicated way to just add EAX to EDX and put it into EAX. So it's going to add those together. Then it's going to add 1 to EAX, right? And so how does callee pass the return value to main?
I know, like in MIPS, you have to put your return value in a specific register to return.
Right.
I'm guessing the same thing happens here?
Yes, which register?
EAX.
Yes, EAX. And where's our return value? Yeah, in EAX, right? We just did all this calculation. We're putting this value here, and now we're done, right? We did return a plus b plus 1. Well, we've done a plus b plus 1, and now we need to actually return that value here. So we have to make sure, right? We got to make sure that we properly put back this base pointer, right? So we're all done with executing. Now we need to go back to main and have main start executing, right? So we need to make sure we put main's base pointer back, and then we need to make sure we start executing wherever main told us to return to, right, at that memory location. So this is exactly what's going to happen in the epilogue here. So now we're going to pop EBP, which is going to take this value on the stack, copy it into the base pointer. So now the base pointer points back up to main's base pointer. Right? And a pop moves the stack, so the stack moves up 1. And a return instruction is the opposite of a call. It's also, you can think of it as a pop EBP. So take the value on the stack, move it in the instruction pointer, and move the stack pointer up 1. So now we're going to take 804 A3BF, put that into the instruction pointer, and we're going to move the stack up. And now look, everything's perfect, right? The stack is exactly where it was when we call E, right? We have the return value of calling that in the EAX register, and our base pointer was put back successfully, and we're going to start executing right after this instruction. Yeah?
Why does popping EBP make it go all the way up?
This one?
Yes.
Ah, there's 2 pointers here. So there is the, at that point, okay, so before here, both the base pointer is at FD, one more click. Yes, the base pointer is at FD2B0, and the stack pointer is at FD2B0. So this pop EBP is going to take the value that's on the stack, put it into the base pointer, and then move the stack pointer up 4. So this is why now we have the stack pointer will point at FD2B4, and the base pointer is going to be way up there. So that's why it moves that far. It's not that the stack pointer moves that far. So now we have a function call, right? We've called the function, it's done some work. The function, the calling, and the important thing, right, is that the calling convention makes sure that after this instruction is called, everything's in a consistent state, right? The stack pointer is where we wanted it to be, the base pointer is where we wanted it to be, the function did something, the only register, well, that's not 100% true, right? But at least the value that we want is in register EAX. So now we can go back and we can look at, okay, what is main going to do after this function call? Oh man, I have to go back to one. Not 77. All right, if we go back here, now we're going to return A from main. Right, so we're going to set this to a local variable, and we're going to return that local variable. So we're going to move EAX into EBP minus 4. Right? Why EBP minus 4?
Because we allocated all that space earlier, so we
It's
know
the
it's
local
free.
variable A. Right? Exactly. So the compiler just said, okay, at EBP minus 4, in main is going to be where A is located.
Oh, I see what it is.
Right? So we move EAX into EBP minus 4.
And then it moves it back because it's a return.
And then we have the return instruction, right? So this actually finishes the A is equal to call E 10, 4, right? It invokes it, and then it copies that return value into EAX. And then we have return EAX as the next instruction, right? So then we actually have to take the value that we just had in EAX, take it out of EBP minus 4, copy it back into EAX. And then now we do the leave and return. So now we're done, right? We've executed, main has executed, it's put its return value into EAX. And now it needs to put the stack, the base pointer, everything to when it was called. Right? So the leave is the opposite of these two instructions. So it first sets the stack pointer equal to the current base pointer. So the stack pointer is going to move from here up to here. And then it's going to do a pop EBP, which is going to copy this value on the stack into the base pointer. So it basically gets rid of all the local space allocation that we did here, plus puts the base pointer back. Actually, I think it does all 3 of these. That's cool. Okay, so it's going to move the stack pointer up to the current base pointer, and it's going to pop this value into the current base pointer. And now we're going to leave, right, which is exactly the same thing that call E did, is there's going to be some instruction pointer above us, and so we're going to start executing from wherever they were, and the stack pointer is going to move up. Yes?
So the reason why there is not a leave instruction in the call leave function is because we don't create any space on the stack for local variables.
Yes. So it knows that it's going to be at the same location, so we don't need to move it at all.
Cool.
Yeah. But like why it does, I think it would still be function equivalent. It may be less bytes or something to do a pop EBP than a leave instruction. That I don't know.
x86 now.
Yes.
And the people who make compilers.
And the people who make compilers, exactly.
It's crazy.
Cool, so questions on this? This is exactly this is what happens every time a function is called in your program, right? That program you write, right? This is exactly what happens. Cool. Okay. So, in the example we just had, how were parameters, right, passed to the function?
They put the variables in the stack.
Yeah, it copied, but what did it copy onto the stack? Did it copy like the address of the variable A?
It copies the actual value.
The value, right? Yeah, it copied, it pushed the values onto the stack.
Oh, it's like pass by value, pass by reference.
Yes. So when you invoke a function, right, when you're passing, so now we've looked at a lot of different semantics, right? Now we're going to look at the semantics of parameter passing and the different ways that this can happen. So there's three different approaches we're going to look at. Pass by value, which is the normal thing that you're used to, or should be used to in C and C++. Pass by reference, and pass by name. Right? So these just get into different ways of what does it mean to pass parameters to a function. So pass by value should be kind of similar to the way you think about it, right? So you are passing the actual values at function invocation time. So the values are calculated and then copied to the function, right? So the function receives a copy of those values that are passed in. And we just saw exactly how that's done for C, right? In that example, that showed us how a copy of the values are placed on the stack for that function invocation. So if we look at like a very simple example, so here we have a main variable x, we have a function int main, we have a local variable y is equal to 4, we call test with y, we're going to print out the value of y, and we're going to return y. Here we have function test. Test is going to say x is equal to x plus 5, and it's going to print out the value of x. Right? So this x is equal to x plus 5, which x is this going to refer to?
The parameter that was passed into it.
The parameter. Why?
Because it's more local.
Because it's more local. Is that like you want to eat local
Like
and
if
shop local, but like really local?
I mean, it would be closer in memory, like it would be stored in the function frame of test.
Yes. So we talked about scoping rules, right? So here, this parameter x is in a more local scope, right, than the global x, right? Does this occur both? Is this true both with static scoping and dynamic scoping?
No.
Well, it all depends on the
Yes.
compiler, how it wants to.
In this case, it would be true, right? For both, right? Because dynamic would still look at the closest block if we were to draw that table, which should still be the index and the parameter. So
Yes.
the static, so it would be the same.
Yes. So yeah, even in dynamic scoping, right, we need to look up this x. We first look it up in the local scope, and we see that there is an x declared in the local scope, right? And then if it wasn't there, then we would look it up in whoever called test, right, to see if there's a variable there declared. Same thing with y here, right? This usage of y, static and dynamically, is going to both be the same because it's in the same local scope. Cool. Okay, so if we compile this with, all right, so we compile this with pass by value, right? So this is a pass by value example. So what should this output? I could cover up the thing. So what's the first line that's going to be executed to print out?
The one test.
The one in test. So what is this going to output? 9? So 4 is set to the local value. Oh, all right, sorry. 4 is, the local variable y gets the value 4. Then we're passing by value, right? We're copying 4 into test, right? So that the formal parameter of test, this x, it has the value 4. And then we set 4x is equal to 4 plus 5, which is, yeah, it was a softball. 9, right? So we print out 9 first, then test returns, and then this prints out the value of y. So what does this print out?
4.
Why doesn't it print out 9?
Because
we didn't update y.
Pass by value.
But we just changed x in here.
That's x.
Copy.
Yeah, so it's a copy of it, right? That's the important thing, is test receives a copy of all of these things. So when you modify that, and we say x is equal to x plus 5, right? We're changing this copy, and we actually saw, so this is exactly how that's implemented and why this works in x86, right? Because this value x is actually on the stack. So we want to invoke this function. We copy whatever's in main of EBP minus whatever where y is. We copy that value onto the stack, so that when test gets it, it gets that new value that's on the stack. And it's not even talking about the same value. So when we execute this, it will output 9 and 4. So we can see if we do a circle box diagram for this, right? We know that, okay, when this executes, y is going to be equal to 4, right? And then when test gets executed, now we're copying that value 4 into the value associated with the variable x, right? So x is going to have the value 4 when this is invoked, but any changes and modifications, like when we have x is equal to x plus 5, that's going to change x, right? But these are completely different boxes, right? They're separate. And then when this returns, now when we print out y, we're just printing out y as 4. That's the value inside y. Okay, great. Everybody get pass by reference? Or pass by value? That was a trick.
Are we going to do like object examples or just primitives?
What's the difference?
I mean, it should be the same thing essentially. But
Yeah.
just extra like
Just more.
to show.
No, we will, because I want to talk about the concepts. I think that muddies things a little bit. So we'll talk about that. We will talk about what is Java. That's where it gets tricky. Okay, so with pass by reference, right? So this is a completely different way to think about this. It's saying, okay, instead of passing a value or copying that value in there, I want the formal parameters of the function to be bound to the locations associated with the actual parameters, right? So this goes back to box circle diagrams, bindings, right? We want to actually bind that name to the location that was passed in, right? So what does this mean if we want to pass by reference? What does this mean about what kind of, when we invoke a function and we're using pass by reference, what does this mean about the parameters that we're passing in?
Would they be pointers?
Would they be pointers? What was that?
Your boxes.
Boxes? What does that mean? Why?
You're passing in the location.
Right, we have to bind it to a location. If it doesn't have a location, then we can't bind it. What's another way for something that, yeah?
Sorry for interrupting. So in the case of, in the last case,
Mhm.
if we were to do it passing it by reference, when you drew the box circle diagram for y, it would mean that we wouldn't change x to 9. We would take the location of y and change that to 9.
Yeah, we'll see. We don't actually even create a new box for x, right? We
So
bind
we
x.
just use the other one, yeah.
Yes. Yeah, so what does it mean when something has a location associated with it? It's an L value? Yeah. So the actual parameters, so they must be L values, right? When we invoke a function, we have to pass in L values, right? We can't pass in 10 because 10 has no location associated with it. So if we change that, what does that mean, right? That doesn't make sense. So let's look at an example of pass by reference. Same example, we have an X, we have a main, Y. Right, so this is a C++ example, I believe. So you can put, you can choose how you want references to happen in C++. Other languages, maybe it's always passed by reference, right? It could be always passed by value. So this is one of those semantic things that really depends on the language itself. Okay, so I can compile this. Is it going to compile?
Yep.
Yes. When I run this, now what is it going to output?
9, 9.
9, 9. 9. Okay. So it's going to output 9, right? So this is exactly the same thing that happened the very first time we saw this, right? It's going to output, it's going to pass in 4, right? X is going to be 4. It's going to be 4 plus 5 is 9. It's going to output 9, right? So the big difference here is what happened when test returns, because we assigned to X one of the parameters that was passed by reference.
It's going to output 9 because we
Exactly.
didn't make a copy.
Yes.
We're actually using the original.
Yes. So it's going to be 9. So if we look at it with box circle diagrams, right? So we have Y. We're going to copy the R value 4 into the location associated with Y. Then when we invoke test, right, X is passed by reference. So it's going to be bound to the same location as Y. Right? Now when we say X is equal to X plus 5, we're changing the value in the location associated with X, which is here. Right? And then when we print out Y, we print out 9. So is this useful?
Could be.
Why?
I know if you use pass by reference, you can have basically more than one return value, which can be very convenient.
Yeah, more than one return value. So why would you want more than one return value?
Any number of reasons, really. Lots of different reasons.
Well, how does this get you more than one return value?
Because you can pass multiple things by reference. So if you create, like, let's say you want to pass out 3 values and you just create them before you call your function and pass them by reference, you have access to all 3 of your variables.
Right, so does everybody see? So do you strictly need pass by reference to do this?
No.
No.
How could you do it otherwise?
Structures,
Yeah, you could create a structure that gets returned with the values that you want, right?
global
That's just more-
variables.
that's just more- that's
You
just
could use
more-
global variables. That'd be a little dirtier though.
That's a lot of
Right? So yeah, actually, and to be completely honest, nicer languages actually will allow you to return multiple return values. Right? So that kind of actually gets around even needing to use this because
What languages do that?
Python.
Does it?
Yeah, so actually it's most of them, so it's all a question of can you do it? Yes. So like, but a lot of it is you return a tuple, right? Which is kind of cheating.
Not
But
really. It's one thing that contains several things.
yes, but it also, the language actually supports it a lot better. So you can do, let's see. You can do something like, so the language actually helps you support this, right? So this is, if this returns a tuple, it returns the first, it sets the first one into first and the second one into second.
Okay, that's
So that way, it's kind of under the hood, it's all tuples, but
doesn't really matter.
yeah, exactly. At least from calling it, it looks nicer. Yeah.
So why do languages like C++ and Java not support that?
Because they're pretty.
They're older. You could still do this. Doesn't C++ have like a pair class? I think there's also a tuple class in C++,
They have a pair
right?
class,
So
yeah.
maybe the newer versions. So they are slowly getting there. The other reason is they provide band-aids like references, right? So you can pass variables by reference, and that's actually the style of doing C and C++. Is that's like style, and I guess you can consider it fashion, is kind of a huge part of programming languages, right? It's like if everybody who programs C is used to doing it in this way, well then you don't do it in some new different way because people aren't used to that, and so they don't understand what's going on. Yeah, other languages, what other languages do this?
Swift.
What was that?
Swift.
Swift? Oh, nice, cool. Did not know that. Yeah, it's one of those things that's more of a it's more of a syntactic thing because you can just translate all of this to tuples, right? But it's nicer as a programmer to be able to do this because you can write functions that return different things. I guess it's also really used in C, especially because dealing with lists. So oftentimes you not only need to, if you call a function that creates a list, you need to know, you need a pointer to that list, and you need to know the size of that list, right? So that you can properly deallocate it and everything. So that's another big area. What were we talking about? References. Yeah, cool. Okay, cool. So now, okay, barely have enough time. Okay, that's fine. Now we're going to talk about pass by name. So this is going to be something that is going to seem crazy. So it's, I actually think it's important to learn about it to understand, like, okay, this is how crazy you can go with design. And actually there are practical reasons, like it's actually easier to implement pass by name than pass by reference or pass by value, or it can be. The idea is when you invoke a function, you do a textual replacement of all of the, inside the function, all of the references to the actual parameters are replaced by whatever the formal parameters are. No, switch that. The formal parameters are replaced by all the textual expressions of the actual parameters. So yeah, so the formal parameters in the text of the function are replaced by the text of the actual parameters everywhere in the function and every place that they occur. So let's look at an example. So same example. So what's going to happen is when this test function is invoked with pass by name, all of these x's here and here, they're all going to be replaced with y's. With this text here. So it's going to be y is equal to y plus 5 and print out the value y. So let's say we have some GCC compiler that actually uses pass by name, right? It's going to execute, so what's the output going to be? 99, just like references, right? So
what's the difference between this and pass by reference then?
yes, so the other important thing to note is that this function, these y's, right, actually have access to this scope, right? So they reference that y. This is not this y here. This doesn't shadow anything. This basically, you can think of it as if you took this function test, the lines in here, and replaced them here with test, and by changing every x to be y in here.
So
yeah, in the back, just like, let's go here.
Isn't this just like a global variable? Like the same acts just like a global variable, doesn't it?
Not quite. I don't. You mean the x of the parameter to test?
Well, like
The
a
function
y.
test?
Like it's just like using a global variable y and using it in.
It actually gets even crazier. So, I think. Let's go with this here. Yeah.
Okay, this sounds similar to preprocessors.
Mm-hmm.
Okay.
Yeah, it's actually how it was done, and that was a lot easier to do it that way, because you could just kind of replace that function in line. You could actually easily inline every function call. I guess unless it was a recursive one, but yeah.
So you said it makes a copy of it.
Kind of, yes.
So it doesn't.
That's the way I think about it. Is it like every invocation of this function is kind of different because it depends on what you actually invoke that function with. Like the structure is still going to be the same. You'll always have something equals something plus 5, and you'll print out something. But whatever that something is replaced by whatever the text here is of this invocation. I think there are more hands. Okay, so let's look at a more complicated example. So here we have a global variable I, an array A. We have a function increment, which increments I and then increments X. We have a function main, we set I to be 1. Right, so what does this I refer to?
The global.
The global I. Right, and this X refers to this parameter X. So we set I is equal to 1. We say A1 is equal to 1. We set A2 equals 2. And then we increment AI. And then we output I and A1 and A2. So what is it going to output?
How are we,
This is pass
how are
by
we
name.
passing?
Pass by name. Pass by name.
I can't see it. Passing A1.
what this function increment looks like, right?
Oh, because it has
Yes, so it passes in AI. So AI is not evaluated at function invocation time.
right. It's not
AI happens wherever X appears, and every place X appears, A bracket I occurs. So what this, essentially this copy of this function is going to do, is going to do I++, and then it's going to do AI++.
Weird.
Yes. And you see that just by switching the order of these two, it's going to do something different. So if we could compile this, we would run it, and it would output what? So what's I going to be? 2. Definitely going to be 2. What's A1 going to be? 1. And what's A2 going to be? 3.
Wow.
Yeah. Yes.
So this is just literally an inline function, right? Is there any,
I can't imagine that would be useful.
like under the hood, is there anything different about it?
Right.
Well, even when you inline functions, right? I mean, with C or C++, they'll do it so this doesn't happen.
Oh.
So it's kind of like, it's like textual inlining, like preprocessor inlining in some sense. Yeah.
Why doesn't it pass AI while I is 1 is A1? Like,
Because this is it, so it's not, so the invocation of this function, it doesn't evaluate that expression and then copy the value in there. It textually replaces all instances of this X with whatever you put here. So it's not actually evaluated when you invoke the function.
So since you're passing in that I variable with invocation.
Yes, so it means that this I is evaluated, whatever AI is evaluated at this execution time here for this X.
Soup's weird.
Yeah, yeah, it gets really weird, and it's really cool. And actually, the other thing is you can actually easily emulate this using pass by value and pass by reference, which is also kind of cool. But all right, so we will stop here. We'll go over this a little bit more on Wednesday.